Okay, so I'm going to pick it back up where where I left off on page 14. We're taking a look at points of inflection, and this is where the second derivative changes from positive to negative or negative to positive. Okay, so example 3, we have y equals e to the negative x squared. So we're going to go first, do e to the negative x squared, and then we're going to multiply by the derivative of the exponent, which would be negative 2x. That's using chain rule. So I'll just kind of rearrange some things. So that's really negative 2x times e to the negative 2x. Now I'm going to use, for the second derivative, I'm going to use the product rule. So we'll have negative 2x and then times the derivative of e to the negative x squared, which is e to the negative x squared times negative 2x, plus, and then we're going to have negative 2, that's the derivative of negative 2x, times e to the negative x squared. So I have here positive 4x squared e to the negative x squared minus 2e to the negative x squared. I can factor out, so I look at what I can factor out of each term. I have a 4 and a 2, so I'll take out a 2. And then I have an e to the negative x squared in both parts. So when I take that out, I'm left with a 2x squared and then minus 1. Now remember, this is still our second derivative here. So when I look to see where the second derivative is equal to 0, so the first part will never be equal to 0, right? Because that's e. However, if I take a look at the second part, the 2x squared minus 1, set that equal to 0. So we get 1x squared is 1/2, which implies x is going to be equal to positive and negative 1 over root 2. If you want, you can rationalize that to the square root of 2 over 2, but you don't need to. Okay, so I'm going to create my number line. Now remember, when I do the number line, if I'm doing points of inflection, I'm looking at just the second derivative. So I'm just looking at plugging it in here. So I'm going to put negative 1 over root 2 and positive 1 over root 2. So I can pick something to the left of negative 1 over root 2. It doesn't really matter. You can pick negative 2 and plug that in. Now keep in mind, this part here, that's always going to be positive. So we're really just looking at the 2x squared minus 1 and seeing what we get here. So if I plug in something over here, say negative 2, that's going to give us something positive. So it'll be concave up. And then we can pick something in between here, and that will be 0. So that's going to give us a negative 1. So negative, that's going to make that concave down. And then plug something to the right, that's going to give us positive. So it's going to be concave up. So everywhere it switches, so we can see the points of inflection are, well, if I plug in negative 1 over root 2 back into the original equation, that's going to give me 1 over, it's going to give me e to the negative 1/2, or 1 over square root of e. And I'll get the same thing when I plug in positive 1 over square root of 2. I'll get 1 over square root of e. So those are my answers. Let's look at another example. Now this particular example, I would not use product rule. I would distribute first, just to make that a little easier. So we have 4x to the third minus x to the fourth. So my first derivative is going to be 12x squared minus 4x to the third. Again, we're looking for the second derivative for concavity, so that's going to give us 24x minus 12x squared. I'm going going to factor this, so I can take out a 12x, and I'm left with a 2 minus x. So setting this equal to 0, I get x equals 0 and x equals 2. So I'm going to create my number line. I'm going to label it. This is my second derivative. I'm going to place 0 and 2. So if I pick a value to the left of 0, say -1, I'm going to get a negative, so that's concave down. Pick something between 0 and 2, say 1. Plug that back in, we get positive, so that'll be concave up. And then pick something to the right of 2, say 3, and that's going to give us negative. So I'll be concave down. So I have points of inflection. They're going to be, well, if I plug 0, remember to get this y coordinate, I may not have been very clear on the last one. In order to get the y coordinates for my points of inflection, just keep in mind that you're going to plug, you know, the x value, which was positive and negative root 2, back into the original equation. Anytime you're looking for an actual point, like when we were looking for maximums and minimums, or when you're looking for a point of inflection, we're talking about the original curve. So what you're doing is you're basically finding where they occur by doing the derivatives, and then to find the y coordinate, that's going to plug back into the original. So we're really looking at, you know, when we go back, once we're looking for the points of inflection, go back to the original. So when I plug in 0, I get 0. And when I plug in 2, so I get 4 times 8, so 32 minus 16 is 16. So here are my points of inflection. Okay, so taking a look at the next page. We want to use the graph of f. This should really say an f here. But we're going to use that graph to estimate where f prime and f double prime are 0, positive, and negative. Okay, so let's do part A. Now remember, this is the original. This is the original graph. You always want to take into consideration what type of graph you're starting with. So in this case, I'm looking at f prime. Now f prime, we're looking at increasing, decreasing. Or you can look at slope. Remember, the derivative is the slope of the tangent. Again, we're going to just approximate, you know, here. So we're going to say, let's look at where f prime is equal to 0. Okay, because that's, we can see that there's going to be, you know, a horizontal tangent about here. Again, we're approximating. It's not right at 1. It's like maybe 1.2 or negative 1.2. We'll just say to make it easier, we'll make it, we'll say that x is approximately -1, and at 1 we have horizontal tangents. So again, we answered the first part, so that's where it's equal to 0. Where is f prime of x greater than 0? So that's going to be on the interval. So I'm looking at a positive slope, or where it's increasing, right? So if I look at where it's increasing from -1 to 1. And we can use brackets for that, or remember how I said that to discuss increasing and decreasing, you could use parentheses would be fine also. Then this, where do we have less than 0? So that's that. We're going to look at where it's decreasing. So that's going to be from -infinity to -1 union, and then 1 to infinity. And then for part B, now we want to consider f double prime. So remember, when we're looking at the original graph, we're going to look at the concavity. Okay, so where it's concave up and concave down. So now when I look back at my original, it looks like, if I had to judge this, it looks like it's going to be concave up until we get to 0, because then it switches to concave down. So I'm going to say that it looks like f double prime is equal to 0 at x equals 0. F double prime of x is greater than 0, so we're looking at where was it concave up. Looks like it was concave up from negative infinity to 0. Remember, we use parentheses for the concavity always. Increasing and decreasing, we can use brackets. And then the second derivative is less than 0, where it's concave down, and we can see here it's concave down from 0 to infinity. Okay, next one. Now we're going to use the graph of f prime, so I should have labeled this as f prime. We're going to use this graph to estimate the intervals on which the function is increasing or decreasing, and then we're going to estimate the values, the x-coordinates, excuse me, of all the local extreme values. Okay. So we are going to look at, first of all, let's look at the derivative. So I can see at -3 and at 3, these are places where the derivative changes from being above the x-axis to below, or below the x-axis to above. Remember, we're looking at the derivative graph. So where is f prime positive? Well, from negative, it looks like negative infinity to -3, it's positive. It's above the x-axis. And then from -3 to 3, even though it looks like it touches the x-axis right here at 0, everything it doesn't cross. Okay, so we don't include that value. We only include the value when it actually crosses the x-axis. So everything stays below. So we're going to put in a minus. And then at 3, it crosses over and becomes positive. So I'm going to draw remember this is the first derivative, so we use my little arrows. So I can see there's going to be a maximum at -3 and a minimum at 3. So for part A, we can answer where is it increasing. Okay, so increasing is from negative infinity to -3, and then from 3 to infinity. And then for B, where is it decreasing? So again, we don't really count the place where it just touches the x-axis. Everything stayed below, so we're going to say from -3 to 3 is where it's decreasing. And then finally, we're going to estimate x-coordinates of all the local extreme values, which we just did. This is why we do this little number line, because it makes it really clear. It makes it really easy to see based on how we interpreted the positive, negative numbers and then drew in the arrows. So I can see there's going to be a maximum at x equals -3 and a minimum at x equals 3. We don't know the y-coordinate. We don't have enough information to find out that y-coordinate at this point. Later on, we will find out a way to determine that, but until that, we can only find the x value. Example number 6. A particle is moving along the x-axis with the position function x of t equals 1/3 t to the third minus 5/2 t squared plus 6t plus 4. And t, of course, is greater than or equal to 0. So we want to find the velocity and acceleration and describe the motion of the particle. So let's do velocity first, which we know is going to be the first derivative. So we get 3 times 1/3, so that'll cancel, and we'll just get t squared minus, and then we get 5t, and then plus 6. So there's our velocity, and then we'll do the acceleration, which will be the derivative of velocity or the second derivative of the position. So we get 2t minus 5. Okay, so here's our velocity and acceleration. Right now we want to describe the motion of the particle. So we're going to use the velocity to do that. So I'm going to take my velocity and see if it factors, which it does. It's going to be t minus 2, t minus 3. So when I set that equal to 0, we know that's going to give us 2 critical points. So basically 2 and 3. So here's my velocity. So here's 2 and here's 3. And remember, you can't plug anything smaller than 0, so think of that as our left endpoint. So if I plug in, say, 1, I'm going to get a negative times negative, so that would be positive. And then plug in, let's say, 1.5, or I'm sorry, 2.5. So that'll give us a positive times negative, which is negative. And then plug in something bigger than 3, say 4, positive times positive is positive. So the way we would describe the motion of the particle, so the particle oh goodness, if I can spell correctly. So the particle moves in the positive direction. Well, actually, let's say to the right. So the particle moves to the right from 0 to 2 seconds. Then it moves left from 2 to 3 seconds, and then moves right for t greater than 3 seconds. So for right now, if they ask to describe the motion of the particle, just take a look at velocity, find the zeros for velocity, and then put it on a number line. Use test values, and where it's positive, you could say it's moving in the positive direction, or you could just say moving to the right, and then if it's negative, moves in the negative direction or to the left. Okay, so second derivative test for local extrema. We don't use this one too often, but it is a neat little theorem that we can use to determine a local max or local min using second derivatives. So one of the things we need to make sure first is that it's a critical point so if it's a critical point, so f prime of c is equal to 0, and the second derivative is less than 0, meaning it's concave down, right? So basically we're saying there's a horizontal tangent, that's what this says, and it's concave down. So if there's a, right, here's your horizontal tangent, concave down, so you can see that that's going to have to be a maximum. And our example is negative x squared, right? So negative x squared, we know what that looks like. It kind of looks like that graph I just made. So let's just show how this would work. We're going to do the derivative, which will be negative 2x. And so the second derivative, I get negative 2. So I can see that that second derivative is less than 0. And from the first derivative, I can see that I get a critical point at x equals 0. Okay, so as I was saying, that when we have the second derivative, so f double prime of 0, so we basically plug in that critical point. And now, honestly, it doesn't matter what we plug in because we can see it's going to be -2 no matter what. So therefore, there's a max at f of 0, which is going to be equal to 0. Okay, so then our other example is, let's say we have a horizontal tangent and it's concave up, right? So again, this one was a horizontal tangent and concave down. So if these two things apply, then that means we have a maximum. And over here, let's say we have a horizontal tangent and it's concave up. Okay, so that's going to mean that we have a minimum. Okay, so again, it's like, right? So that means we have a min. This one had a max. So here when we do the derivative, we get 2x. So just showing our critical point would be x equals 0. So now when I do the second derivative, we get just a 2. So obviously if I plug in our critical point, I still get 2. So therefore there's a min, and this is going to be at 0, and we get 0. So we're going to use that second derivative test to find the local extrema for this function x to the third minus 12x minus 5. Again, this is just a different method to using that first derivative and then plugging back in. This is just another way of doing things. So we'll do the first derivative. We get 3x squared minus 12. And then just, actually, let me do let's do the critical point. So let's set this equal to 0. I factor 3 out, and we get x squared minus 4, so that would be x plus 2, x minus 2. So I do get my critical points of -2 and +2. Now, over here, let's do the second derivative. So that's going to be 6x. And then what I want to do is I want to plug in, since we have -2 was one of our critical points, so 6 times -2 is -12, right? So if it's negative, this means that we have a max. What's the max? Well, that's going to be f of -2 plugged back into the original, so, which I didn't figure out ahead of time. So -2 to the third minus 12 times -2 plus, minus -2 to the third, I'm going to try this again, minus 12 times -2 minus 5, so we get 11. And then when I do the second derivative and plug in my other critical point, which is 2, I get a positive 12, so since that's positive, we know it's a minimum, and our minimum is going to be f of 2. And I get -21. Okay, the last example, we want to identify where the extrema of f occur. Notice that we are given the first derivative. We want to find intervals on which f is increasing and decreasing, and then find where the graph of f is concave up and concave down, and then we're going to finally sketch a possible graph for f. Okay, so let's start with A. Again, we don't have the original equation, we just have the derivative. So if I'm given the derivative to start, what do we want to do? Well, we can start with just finding the critical points. So to do that, I'm going to factor this first. I can take out a 4x squared, and I'm left with an x minus 3. Okay, so when I set this equal to 0, I get critical points at x equals 0 and 3. So I'm going to make my f prime number line. And my domain here is all reals. So I can plug in, let's say, -1. So I'll get a positive times a negative, which will be negative. Then I can plug in, let's say, from 0 to 3. Let's say, it doesn't really matter, I can plug in a positive 1, so we'll get positive times negative, which is negative. And then plug in something, say 4, I'll get positive. Okay, so when we look at our number line with f prime, we see it's going to decrease, continue to decrease, and then it's going to increase. So therefore, there is only a minimum. So for part A, there's a minimum at x equals 3. Now for B, we actually did the work for that already. So using that same number line, I can see that it's increasing on the interval from 3 to infinity, and it's decreasing. Now again, since it did not change direction at 0, we just include that in the interval. So it's actually just going to be -infinity to 3 bracket. Okay, next part. Find where the graph of f is concave up and concave down. So for part C, we need to do the second derivative. So we go back up to the first derivative, which was 4x to the third minus 12x squared, and we do the derivative of that. So that's going to be 12x squared minus 24x. So I'm going to factor out a 12x, and I get x minus 2. So solving the second derivative equal to 0, so we get x equals 0 and 2. So now my second derivative, so here's f double prime at 0 and at 2. So if I pick a value to the left of 0, say -1, again, we're going to plug into the second derivative here. So I get -12, -3, so that'll be positive. And then plug in something between 0 and 2, say 1. That's going to give us negative. And then plug in from something bigger than 2, say 3. That's going to give us positive. So it's going to be concave up, concave down, concave up. So we're going to write that out. So it's concave up from -infinity to 0. Oops. And then also from 2 to infinity. And then we see it's going to be concave down from 0 to 2. And then finally we want to sketch a curve. Okay, so I didn't provide a graph here because when we're trying to come up with the graph for f, all we have to base our graph from are the x coordinates. So we can only look at what's happening with our first derivative and second derivative in terms of where it's decreasing, increasing, and concavity. So sometimes it helps to make the number lines kind of on top of each other just to see what's happening. So like here's my f prime, and then right underneath that I'll put f double prime, and I'll try to like match things up. So for example, we had at 0, we saw that if we look back up here, it was a decreasing, right? It went down, but it was also concave up. And then I'm just going to put 2 on our number line, and then 3, because from 0 to 3, it was decreasing, so it's like decreasing, still decreasing. But from 0 to 2, it's concave down, right? This was negative here. Oops, I forgot to put in my concavity. Let me put that in. This is going to be concave up and then concave down. And then from 2 on, it's going to be concave up. And then here, after 3, it started increasing. So we know that there's a minimum at 3. Okay, so here we go. I'm going to create a graph. I'm not going to put any y coordinates. I'm just going to show my x-axis. And I'm going to put 0, and I'm going to put 2, and I'm going to put 3 on the graph. Now, your minimum value is at 3. That's all we really need to be concerned about. So you can put the minimum wherever you want it. It really doesn't make a difference. You just want to have the graph, so it's going to be decreasing, but it's going to be concave up. And then at 0, it's going to be concave down, but there's no maximum or minimum. And then, so it's going to be something like this. It's going to be concave up. That's really bad. Let me try again. Okay, there's going to be concave up, and then concave down until we get to 3. And then it's going to be concave up from 3 on. So it kind of like switches here, and then it goes down to -3. So -3 is a minimum. That's a really rough sketch there. But, you know, and as you can see at 2, somewhere at 2, it's switching from concave up to concave down. Again, just a rough sketch.